Okay, in this exercise, I would like to explore some applications of the central limit theorem. But rather than just doing problems specifically related to the central limit theorem, I want to do some normal probability distribution problems as well to see the similarities and how we can tell the difference in terms of when to use what approach. Okay, so number one, in a study of facial behavior, people in a control group are timed for eye contact in a 5-minute period. Okay, their times are normally distributed. Right, that's important. With a mean of 184 seconds and a standard deviation of 55 seconds, for a randomly selected person from the control group, find the probability that the eye contact is greater than 230 seconds. Okay, and 230 seconds apparently is the mean for paranoid schizophrenics. I always recommend just drawing out a quick sketch and doing a little labeling to sort of avoid any careless mistakes with these types of problems. So I have these 6 blank normal distributions over here to the right. Okay, so for number 1, we're dealing with a normal distribution with a mean of 184 seconds, standard deviation of 55 seconds, and we want to know the probability that x is greater than 230. Okay, greater than means area to the right. Remember the correlation between area and probability when we're dealing with continuous probability distributions. Okay, so the probability that x is greater than 230 will be that area shaded in red. Now, Excel cannot give you that red shaded area. Excel could only work with area to the left. So Excel could give you this green area. So if we want that red area, well, we know that this is a probability density curve or graph used for continuous probability distribution. So the green area plus the red area has to add up to 1, so we could use the rule of complements. So the red area should equal to 1 minus the green area. Okay, so let's use Excel to calculate that. So we need to start with an equal sign, 1 minus, and it's the normal distribution function in Excel that will give us the area, norm.dist. And now Excel is asking us for the x value, which is 230. It is asking us for the mean, which is 184, the standard deviation, which is 55, and then that last question, cumulative, yes or no, with continuous distributions. With continuous distributions, it's always yes. And so 1 means yes. In Excel, you could type the word true or use the word 1. Okay, so that's 1 minus the green area, should give us the red area, which is the probability that x is greater than 230 seconds. All right, looks good. And I'm going to include it here. No, that didn't work. I'm going to include it here as text, just so in the blue cell is where Excel is calculating the area, and above it in white is just the text that I used to calculate the answer. All right. Number 2. In one region, the September energy consumption for single-family homes was found to be normally distributed with a mean of 1,050 kilowatt hours and a standard deviation of 218 kilowatt hours. For a randomly selected home, find the probability that the September energy consumption level is between, that's important, between 1100 and 1225 kilowatt hours. Now, keyword here is between. Okay, so let's come over here to the graph. For number 2, we're given that the mean, the center of the graph here is 1050. We're given that the standard deviation is 218. Now we're looking for the probability that our random variable takes on a value between 1100 and 1225. So we're looking for the area under the graph between these two x values. Okay, now again, Excel can't do area between. Excel can't do area to the right. Excel can only do area to the left. So what we could do here is we could take all of the area to the left, of 1225. Excel could do this, but that's too much. That's more than we want. Okay, so for that we use the normal distribution function equal norm dot dist. X value is 1225. The mean is 1050. The standard deviation is 218. And cumulative, yes, we're using that. Now, that's too much area, so what we have to do is now subtract off the area to the left of 1100. Okay, so we could subtract off. We'll use the same function, norm.dist. And now our x value is 1100 with a mean of 1050, a standard deviation of 218, and always, always we are saying yes to the cumulative function for continuous distributions. Okay, so what we basically did here was, let me use, let's go with blue here. So we took that green area minus the blue area, and that left us with the area shaded in red. Okay, so let's put our text here just for a reference. You know, it's not necessary, but for purposes here, it's probably not a bad idea. Okay, so number three. A bank's loan officer rates applicants for credit. Okay. These ratings are normally distributed with a mean of 614 and a standard deviation of 51. Find the 60th percentile. And remember, percentiles are locations that separate 1% of a set of values from the remaining set of values. We want the 60th percentile will separate the lower 60%. Okay, so we know this normal distribution graph, the total area is 1 or 100%. It's symmetric, so it's 50% on the left, 50% on the right. So 60% will probably be somewhere over here. Okay, and we're given that the area in here is 60%, but what we don't know is that x value that separates the lower 60%. Okay, so this is a sort of the opposite case as numbers 1 and 2. In numbers 1 and 2, we were given the x value, looking for the area. Now we're given the area, looking for the x value. So that's the opposite of the normal distribution function, or the inverse of the normal distribution function. So we'll use the Excel function norm.inv for inverse. Oop, not there. Equal norm.inv. Now see, it says returns the inverse of the normal cumulative distribution for the specified mean and standard deviation. Okay, so remember, probability and area, these two terms mean the same thing in the context of, just here in the context of continuous probability distributions. So our probability, or our area, is 0.6. The mean is given as 614. The standard deviation is given as 51. Okay, so this should give us the x value that separates the lower 60%. And we should probably, just for the sake of referencing later, 614 is the mean, and the standard deviation is 51. Okay, let's record our, again, it doesn't seem to work that way. Okay. All right, looks good. Moving on. So for number 4, it's nothing to calculate here. Number 4 just says read problems 5 and 6 and explain which problem, number 5 or number 6. They're both relating to the same situation or scenario. Would you expect a higher probability in number 5, or would you expect a higher probability in number 6? Now let's think about this before we do any calculations. In number 5, suppose replacement times for washing machines are normally distributed. Okay, we have normal, and this is important. It can't be assumed. Normally distributed with a mean of 9.3 years and a standard deviation of 1.1 years. Find the probability that a single randomly selected washing machine will last 10.5 years or more. Okay, now number 6, same scenario almost. Replacement times are normally distributed with a mean of 9.3 years, a standard deviation of 1.1 years, so same values. Find the probability that a randomly selected shipment of 8 washing machines, so it's no longer a single washing machine, so let's underline this. A randomly selected washing machine, or a randomly selected shipment of 8 washing machines. Okay, so in number 5, we're dealing with a single selected machine. And for number 6, we're talking about an entire group of 8 washing machines. Now, 10.5 years is above average. They're expected to last 9.3 years. So what is more likely, do you think? That one single washing machine lasts, looks like 1.2 years above average, 10.5 or 9 versus 9.3. So would you expect one washing machine to last longer than expected, or would you expect an entire group of 8 of them to, on average, last longer than the expected 9.3 years? Well, I'm going to say it's more likely that it only happens to one machine rather than the 8. So let's see if we could calculate this. Okay, so in both cases, the mean is 9.3 years. The standard deviation is 1.1 years. And we're looking at 10.5 years or more. Okay, so maybe 10.5 years here, or more, greater than 10.5 years. Okay, so we could approach number 5 the same way we approached number 1. We want area to the right. Excel could only give us area to the left. So Excel could do the green area. So the red area will be, again, 1 minus the green area. So we could say equal 1 minus the normal distribution function, norm.dist. And our x value is 10.5. The population has a mean of 9.3 with a standard deviation of 1.1. And yes to the cumulative function. Okay. Now if we look at number 6, similar question, but now we're applying the central limit theorem. And the central limit theorem, so this is sort of a result of our previous discussion on sampling distributions of the mean, and really the central limit theorem is one of the most sort of monumental or powerful results in all of statistics. What the central limit theorem says is that for any distribution, not just normally distributed populations, but for any distribution, the distribution of sample means. Now that's what we're talking about here in number 6, the mean of a sample. We have a sample of 8 washing machines. And we're talking about the mean of a sample. The mean of the sample means will be equal to the population mean, and the standard deviation of the sample means will be equal to the standard deviation of the population divided by the square root of n. So if we substitute these two values into our formula for z-scores, then we get z is equal to x bar minus mu sub x bar divided by sigma divided by the square root of n. Okay, we could leave off that mu sub x bar just equal to mu. So the z-score should be the x bar minus mu, the difference between the sample mean and the population mean, divided by sigma over the square root of n. So let's plug these values in over here. I have a sort of nice little template set up. Now our x value, actually this should not say x, this should say probably x bar. And same thing for number 7. So let's just make a quick x bar. Okay, so the sample mean is 10.5 or above. The mean as given is 9.3. The standard deviation is given as 1.1. The sample size, well, that's 8. And so our z-score, well, let's just, so what we're going to do here is take this z-score formula and use it right here. Okay, so the z-score should be equal to, I'll put the numerator in parentheses, x bar minus the mean divided by, and I'll put the denominator in parentheses as well, the standard deviation over the square root of n. Okay, so there's our z-score. And you know what, we could add that text down here, just again as a point of reference for later. Oh, no, we want to change that to text so we could actually read it. Okay, so there's our z-score. And we want the red area, so that's 1 minus the green area. Now again, I know we've stated it a couple of times already, but Excel can give us this. So our red area should be 1 minus the green area. But now we've converted to z-scores. So we're no longer using the general normal distribution. We're using specifically the standard normal distribution. So instead of norm.dist, we need to do norm.s.dist. The .s is stating to Excel we're dealing with the standard normal distribution. Now remember the mean is always equal to 0. Standard deviation is always equal to 1, so Excel doesn't need those values. Only needs the z-score and a yes to the cumulative question. So it looks like a much lower percentage. 1/10 of 1% chance versus the almost 14% chance of a single machine. All right, and that should make sense because something out of the ordinary happening once is much more likely than something happening out of the ordinary 8 times. Okay, so let's copy and paste. And this is what the central limit theorem tells us, and this is what we should expect, that something happening out of the ordinary one time is much more likely than something happening out of the ordinary 8 times. All right, one more to go. Let's look at number 7. The weights of the fish in a certain lake are normally distributed with a mean of 20 pounds and a standard deviation of 7.7. Now, if 9 fish are randomly selected, again, this is the indication that we're using the central limit theorem. We're not talking about a single randomly selected object, in this case fish. We're talking about the average. We're talking about the average of a sample of values. Okay, so what is the probability that the mean weight is between 18.6 and 23.6? Okay, so let's come over here to the graph. The fish in this particular lake have a mean of 20 with a standard deviation of 7.7. We want to know if 9 fish are randomly selected, what is the probability that their mean weight is between 18.6 and 23.6. So we're looking for area between these two x values. So we're looking for this red shaded area. So we're going to take the same approach as we took in problem number 2. The area to the left of the larger value minus the area to the left of the smaller value. And again, we have to take this approach because Excel can only work with all of the area to the left. So we just have to work within that context. Okay, so, and now just keep in mind, when we determine that we have to apply the central limit theorem, we have to convert to z-scores. We must convert to z-scores. Okay, so our two values for x bar. It would be 23.6 and 18.6. In both cases, the mean is 20. In both cases, the standard deviation is 7.7, and our sample size is 9 fish. Okay, so same thing as we did down here in problem 6. We need to apply our formula to convert our x bars into a z-score. Okay, so we'll just take the exact same approach. Equal numerator in parentheses x minus the mean, close parentheses, divided by, now the denominator in parentheses, standard deviation over square root SQRT of n. Now in this case, the square root of n is 3, so I mean, I'm typing in, referring to these values. You could type them in directly if you want. Okay, so there's our first z-score, and if we drag this down, Excel will do the same thing for us with that next row of values. Okay, so there's our two z-scores. So we will first get all of the area to the left of 23.6. So that's the, again, inverse function. Or sorry, the distribution function we just used in problem 6. So norm.s.dist, our first z-score, comma 1. And then we'll subtract off area to the left of 18.6. So that's norm.s.dist, and our second z-score, comma 1. Okay, and that will give us the probability that a group of 9 randomly selected fish will, on average, have a weight between 18.6 and 21.3. 23.6. Okay, that about does it for this. I think, it's important to be able to work through the specifics of individual problems, but the reason I wanted to put both the normal distribution problems and the applications to the central limit theorem problems together is to sort of really point out when to use what. So we use the central limit theorem. The central limit theorem we used in number 6 and number 7. And the reason was because in 6 and 7, we were no longer talking about a single object. We were talking about a group of objects. In number 6, 8 washing machines. In number 6, 8 washing machines. And in number 7, 9 fish. In problems 1, 2, 3, and 5, we were talking about an individual person, an individual home, an individual washing machine. Okay, so that's key. That's how we decide whether or not to use this z-score down here, this formula. Okay, that about does it for this exercise.